Hello everyone, my name is Ben Zhang and this is Lab 1 Constant Velocity. The purpose of this lab is to compare the actual position of a moving object at a constant velocity with the predicted position generated by a computational model. The observed object in this experiment was a dry erase marker. We used Tracker to record its positions and compared these to the predicted positions using GlowScript. This lab demonstrates the concepts of Newton's second law. On this slide, I'm reviewing the basic concepts that are essential for this lab. Newton's first law tells us that an object will maintain its state, either at rest or in motion, unless the net force acts on it. This is the idea of inertia. Newton's second law gives us the relationship between force, mass, and acceleration, expressed as F equals ma. It means that the acceleration of an object depends on the net force applied to it and its mass. The idea of constant velocity is highlighted in this lab. If an object moves at constant velocity, it experiences no acceleration, which implies that the net force acting on it is zero. The two equations for this lab that I'll be talking about are the velocity update formula and the position update formula. For the velocity update formula, the final velocity equals the initial velocity added to the net force over mass, multiplied by the change in time. If the net force is zero, we have a constant velocity. Using the position update formula and the marker's constant velocity, we can calculate its position at any given time, as we know both its initial position and the time that has passed. Here's the video of the marker rolling on the table. In the slide on the right, the graph shows our observed model, which represents the actual motion of the dry erase marker in our experiment. Our slope will be negative as it moved to the left of the origin. Our system is the dry erase marker. The surroundings include the desk and the people. Here we have our code and projected model. Since our object started at rest, our initial x position will be 0. We found our initial velocity using the velocity update formula, which should be constant throughout the entire experiment. After analyzing the data from both the observed and projected models, I created a graph to compare them. The most notable difference is that our marker's motion did not follow a perfect linear path like the projected model. This suggests the presence of acceleration, possibly due to a slight downward slant of the table. However, it's also clear that at the beginning, opposing forces like friction and air resistance were the main reasons the marker's positions diverged from the ideal projection almost immediately. These differences highlight how real-world variables can cause significant deviations from an idealized model. The two graphs show a clear difference between an ideal model and our observed results. The computational model based on theoretical and constant velocity produced a perfectly linear graph. However, the observed model's graph was not linear, indicating that the object did not move at a constant velocity. There are two primary reasons for this difference. The first being a manual tracking of the object using the software introduced human error. This type of error, which can be either random due to my inconsistent clicking or a mistake of calibration of the starting point, causing small inaccuracies in the data points and contributing to the deviation from a perfect linear result. The second source of error we could have would be external forces. The most significant factor is an external force like friction. Our ideal model does not account for this force, which systematically opposes the motion of the object, causing it to slow down and resulting in a curved line on the graph. What if we were to flip the orientation of the axes? The graph would change as the slope would change from negative to positive. Because the marker was moving in the negative direction of my original axis, the position was decreasing in a negative direction, resulting in a negative slope. If you flip the axes, the marker would be moving in the new positive direction and its position would be increasing. This would result in a positive slope. Another thing that would change would be the positions. All of the positions would change in sign. For example, a final position of negative 0.260 meters would become a positive value of positive 0.26 meters. Basically, the change in orientation of the axes would change the signs of all of the points and thus change the slope from negative to positive. Our computational model, based on the assumption of a net force of 0 and constant velocity, gave us a perfectly linear graph. This is what we would expect in a perfect frictionless world where there is no net force. However, our observed model was different. It produced a curved line which tells us that the dry erase marker did not have a constant velocity. It was slowing down. This means that in reality, the net force was not 0. This non-zero net force may have caused the discrepancies seen in the graph. In conclusion, the non-zero net force is primarily due to friction and air resistance, which were the opposing motions. Because the opposing forces were not perfectly balanced by constant forward push, the marker's velocity decreased and the net force is zero. Therefore, it is impossible to discuss the number of forces that added up to zero net force in the observation. Thank you for listening.